What is a memory system? If we go back to our pipeline data path, you will see that we've already talked about two different types of memory. One is a register file, which is kind of small. It had space only for 8 words worth of data. And then we had instruction memory and data memory. They are an abstract representation of a memory system. I say they are an abstract representation because a memory system in a real computer is much more complex as it is made of several different types of memory devices. For example, your laptop has probably 3 to 4 different types of memory technologies. So now the question is, why do we need to think about so many different types of memory devices and what do we need them for? Well, we need memory system to store data. An LC2K program, for example, a program written for the LC2K ISA, can access 2 to the power of 18 bytes of data. That's not a lot, but if you look at MIPS program, which is based off MIPS 32-bit ISA, it can access about 2 to the power 32 bytes of data. That's about 4 gigabytes. So that's something. But then if you take a modern ISA like an ARM64 or x86-64, which are both 64-bit ISAs, a program can access 2 to the power 64 bytes of memory. Now that's a lot. That's 18 billion bytes worth of data. The problem is no single memory technology is both fast and big enough to store all of a program's data, especially the ones that are written in modern 64-bit ISA. So our goal is understand the principles behind designing a memory system that is fast, big, and cheap to store a program's data. Now, before we can understand the different memory technologies and construct a memory system, it's worthwhile to think about what properties we can use to reason about these different technologies. Space is obviously an important consideration. Speed is next. We want a memory system to be fast so that if we have a load instruction, it can retrieve the data fast so that it wouldn't stall the data path. We also would like the memory system to be cheap so that your computers are affordable. We also think about a property that allows memory systems to persist data when the power is turned off. We'll see how some of the memory technologies can persist. They're called non-volatile memory systems, and the ones that cannot persist are called volatile memory systems. Now I can take these properties and construct what I call a memory pyramid. A memory pyramid is organized such that the fast devices are placed on the top of the pyramid and the slower devices are placed at the bottom of the pyramid. The top of the pyramid, the fast devices, they're also expensive, and so we cannot afford a lot of them, and so therefore their size tends to be smaller. The ones at the bottom of the pyramid, their cost tends to be cheaper, and therefore their size can be much larger. Now you see that there are different types of technologies mentioned along these three boxes. So let me go through each one of them very briefly so that we can understand their properties a little bit better. The first one is a static RAM, which sits at the top of the pyramid. It's really fast, but it is expensive. It takes about 6 transistors per bit, typically used within a processor chip. They can range from a few kilobytes to a few megabytes, and the latency can vary from 2 nanoseconds to a few tens of nanoseconds depending on the size. And they're expensive. You can probably store an LC2K program's data entirely on an SRAM chip today, but you certainly can't do that for an ARM64 program, as it would take an exorbitant amount of cost to do that. SRAMs also tend to be volatile, meaning if you turn off the power, the data stored in SRAM would disappear. The next technology is dynamic RAM. It sits in the middle of the pyramid. It's much more cost efficient than SRAM, but it's also slower. It can come in sizes of about tens of gigabytes today, but the time to access any data tends to be about 100 times slower than an SRAM access. But they are cheaper, but still not cheap enough to store all of ARM64's program data. And like SRAM, they are also volatile. Next, we have disks. These are made of magnetic hard disks and they have mechanical elements in them. And as a result, they're super slow. They're 100 times slower than DRAM. And remember, DRAM is 100 times slower than SRAM. So we are talking about 10,000 times or more slower than an SRAM. But they can be much larger, tens of terabytes, and they can probably store most programs' data, but not the maximum amount of data that you can access from an ARM64. It's still expensive, and we'll see how to mitigate this later. The other advantage of disks besides cost is that it's non-volatile, meaning you can turn off the power and still have the data persistent. So this is the place where you would typically store your files, like your images, videos, programs, etc. A newer technology that has made it into our commercial computers is flash drives. They're also called, they're an example of a solid state disks. They are increasingly replacing hard disks in our computing systems. For example, today mobile phones and laptops do not have hard disks and they only have solid state drives. They sit in between DRAM and disks in terms of cost and performance. They are still slower than DRAM. They're still slower than DRAM, about 2 to 3 times, but they are as big as a hard disk. They can store today up to a few terabytes worth of data. And so, because of these desirable properties, we see this trend shifting towards SSDs in our systems. Still not cost efficient to store ARM64's data. And like disks, they're non volatile and hence they're a good competitor for hard disks. Here is a summary of all the technologies we talked about. So, at the top of the pyramid, you have static RAM, dynamic RAM in the middle, and then you have a bunch of solutions for non-volatile systems. We talked about solid state disks and hard disks, but you can also think about DVDs and magnetic tapes, which are even more larger in size and more cost efficient. There are newer technologies like DNA storage, which researchers are looking into to make it easier to store even more amount of data, but they also tend to be much more slower than even magnetic tapes. So, what do we desire? Well, we want a memory system that is as fast as SRAM that sits at the top of the pyramid, but we also have space to store all the data that we want. And so we need a system that is big and cheap, like a hard disk. So we want the best of both worlds. How to achieve that? So, to understand how to construct a memory hierarchy, it's worthwhile to think about an analogy from our life. Say you are an avid book reader that uses the library a lot. So, a library is a place that is big enough to store all the books that you ever want to read. But it takes a few hours to go to the library and fetch a book. So, what do? Well, maybe you borrow 20 books or so and keep them on your bookshelf at home. And whenever you need to read a book, you go to the bookshelf. It may take a few minutes. It's still a little bit of a hassle because maybe if you are at school or if you're traveling, then it's a little bit harder to get to those books. So the solution is to have a backpack to store maybe 2 or 3 books that you're reading at the moment. which you can reach into in a few seconds. So this sort of illustrates the idea that I want to use to build a memory hierarchy. Each of these different storage devices, library, bookshelf, and backpack, each serve a purpose. It's not like one is better than the other per se. I need all three of them to have the option to store all the books that I ever want, and at the same time have a solution for me to keep my book that I'm reading and reach to it very quickly. And if you think about a memory system, it's very much like the book example. You have caches, which is similar to your backpack, which is fast and kind of expensive, and so you can have only some data in it. And then you have your main memory made of DRAM, which is sort of like your bookshelf at home. It is a little bit slower, but much bigger than your backpack or cache. And then you have your disk, which is similar to your library that pretty much stores all the data that you ever want your program to access. Now, in order to get the benefit of cache's performance, what we typically try to do is exploit the behavior of a program where we see that most programs they exhibit what's called as a locality of reference. We'll learn more about that later today, but essentially it allows cache to service most of the loads and stores, thereby making the whole system appear to be as fast as this fast device. And once in a while, you reach out to the DRAM and you reach out to the disk when you need to get that rare data. And you bring it back and store it in the cache so that you get to use it in the future. So this is a realistic memory hierarchy now. We also have caches, which is used within the processor, and this is on chip. The main memory is off chip because it's outside your main processor. It sits in a different chip. And your swap space, again, it's your hard disk. And it's used to store any data that spills over from memory. Now, what I have not answered so far is even hard disk, we said, is too expensive to store 18 billion bytes of data because it would take almost $1 billion if you try to do that. So, what's the solution? Well, we are going to fake it. We are going to construct a computing system that promises to the programmer that the programmer can access 2 to the power 64 bytes of data, but we are really not going to have space to store that much amount of data. And the hope is that the programmer will never want to access that much amount of data. Once in a while, that trick fails. And if it does, then you get a window like this, which you may have seen, where the computer complains that your program has exceeded the machine's available swap space on disk. That's why when you buy software, typically they recommend a particular size for your main memory and your hard disk for you to be able to install it. So later on, a few lectures later, we will be tackling this problem under the concept called virtual memory. Now, the memory hierarchy that we talked about is fairly complex. It has several devices, caches, main memory, disk, and it has different latency and size considerations. We don't want to expose these details to the programmer because otherwise programming can become a much more tedious job than it is today. So the solution is the ISA abstracts away all these details away and makes them invisible to the programmer. The only thing the programmer gets to know is the specification of the ISA about how many different types of memory locations they can access. So a 64-bit ISA says a programmer can access 2 to the power 64-bit locations. But the details of the size of caches and main memory and disk, etc., are hidden from the programmer. The view that the programmer gets to see of the underlying hardware is called the architectural view of the memory. The cache is an important part of the memory hierarchy, and we will be spending a fair amount of time understanding its architecture and performance. The term cache commonly refers to SRAM device used within the chip. However, even a DRAM can be thought of as a cache in that it temporarily stores data fetched from a hard disk. But in this course, when we talk about caches, we are referring to SRAM used within the processor chip. So, what is a cache? Well, a cache is used to store data that is most likely to be referenced by a program in the future. Our goal is to try to maximize the number of loads and stores that are serviced by our fast cache and avoid going to the slow main memory. And in the process, we are going to try and improve this metric, which we're going to call as the average memory access time or latency of a store or load. I will define this metric a bit later, but it's a performance metric that we are going to use to reason about a cache's performance. So why are caches important for us to understand? For one, if you look at a modern processor, much of its area is devoted to cache. Nearly more than two-thirds of a processor's die is consumed by caches. Even if you're not a hardware designer, it is important to understand caches because it has a significant impact on the performance of your program. So here is a simple example that illustrates the importance of cache on programs' performance. They both have the same functionality and they differ only very marginally. The order of the subscripts uh, in the array access, yet their performance vary by an order of magnitude. So if you go back to the lecture one, Professor Arthur had explained the differences and did a live demo. I encourage you to take a look. We will also be coming back to this example later on when we talk about spatial locality, which would help us understand the reasons even more in depth.